monumental book. It's going to be in a large format with graphics and the detailed solutions for the drilling operation. So it's designed to teach and show advanced engineers what you need to do for planning. I'm going to let them go through this. They're going to go through this rather quickly, so we're going to ask, and there's going to be questions and sections afterwards that you repeat the question loudly so we can repeat it to the author so they can hear and they can answer your question. They are going to stay later on if you have more, if you want to sit down and talk to Juan and Dr. Leon afterwards. They'll be here. They've got all the time they want this afternoon. Should you need to leave early, then we understand you can leave early, but if you want to stay late and ask questions, they're here to do that. So I'm going to give you just a brief read what they've got here. It's way too modest. Juan Garcia joined Humboldt Oil and Refining Company after graduating with honors from Texas A&M University. During his 39-year career with Exxon, he worked and managed drilling operations in numerous geographic areas, both domestic and international. When he retired in 2005, he was drilling manager for ExxonMobil's worldwide operations. Juan has been an active member of SPE, the API, the IADC, served on several national SPE committees, and on the program committee for the SPE IADC drilling conference. He has authored several SPE and ASME papers and holds several patents for drilling and completions equipment. He's a registered professional engineer in the state of Texas. On a personal note, he's the perfect neighbor. He fixes mailboxes. If you need your golf clubs repaired, he can do the golf club repairs, organizes block parties, and he actually taught the Kingwood Country Club how to cook fajitas. Dr. Leon Robinson. Dr. Leon Robinson spent 39 years with Humboldt Exxon Production Research before he retired in 1992. He made contributions in many technology areas such as mud cleaners, explosive drilling, drilling data telemetry, subsurface rock mechanics, modular mud systems, drilling and hydraulic optimization techniques, tertiary oil recovery, on-site drilling workshops, worldwide drilling fluid seminars, and rig site consultation. He currently is teaching drilling sources for PetroSkills. He also serves as chairman of the IADC Technical Publications Committee, is an API task group leader for solids control, and is a member of the AADE National Fluids Conference Planning Committee. He's been awarded 39 U.S. patents, 22 international patents, the 1985 SPE Drilling Engineering Award, the SPE Legion of Honors 2003, and has received service awards from AADE, API, and IADC. And on an environmental note, and animal purists and activists, he is a friend to small animals in the world and has been known to relocate possums in the local neighborhoods out to the wild again where they can forage and be happy. So with great pleasure, Juan, you're going to kick it off? So you're going to start here? You're going to start? Juan Garcia is going to start. Dr. Leon will follow, and so y'all continue eating and enjoy your meal. Juan Garcia.
Robert, it was Mexican rice, not fajitas. Anybody can cook fajitas. All you got to do is put them on the grill and throw them up.
Yeah, well, they screwed them up.
Well, good afternoon, I guess. No, yes, it is afternoon. And thank you for inviting Doc and me to speak with you today to introduce a new book that he and I are co-authoring on the subject of well-designed planning, construction, and critical operations technology execution. As presented in the SPE newsletter announcement, the book is one in a series that's sponsored by IADC on various drilling-related topics with the objective of producing what they're calling the Encyclopedia of Drilling. The Driller's Knowledge Book that we will give you a brief highlight of today has the objective of giving the reader information that they can use to help design and execute complex well operations safely and efficiently. This slide shows the table of contents for the book. As noted, the first two chapters are on well architecture and construction design. Subsequent chapter topics cover the application of operational procedures used to apply various combinations of technologies aimed at enhancing the continuous improvement of performance. These chapters use complex examples to help explain how to use both the data that we have available prior to drilling a well, as well as the data that's actually collected as well as being drilled, and to optimize the well construction process. I will begin by discussing the topics of well architecture and well construction design, and then Doc will address the application of a combination of several technologies listed in the topic outline. When I was preparing for this presentation today, I decided that the real purpose should be to give you an idea of what the book is about and what is novel and different from other published works, and not about teaching a class by getting too deep down into the weeds with the details. Taking the line from Nancy Pelosi, if you want to know all the details about how to do the math, design curves, and material selections, you're just going to have to buy the book. Well, architecture design is the process of selecting casing setting depths and sizes, and the selection of tubulars to meet the design pressures and the loads for drilling and producing a well. Well architecture is driven by formation pressure, fracture gradient versus depth, well anomalies, well utilities such as what size tubing and production casing we actually need to produce what we expect to find, and obviously also regulations. This is a slide, oops, went too far. On this slide, we show a typical core pressure and fracture gradient curves that are for a complex shallow well or one that would be on land. The curves are constructed from geologic and geophysical modeling data and or from well analogs where they are available. These pressure curves are expressed in pound per gallon equivalent on the horizontal scale and depth per 1,000 feet on the vertical scale. The core pressure curve that is shown here versus depth, when red at the top, is the equivalent pounds per gallon that you would expect those formations to be at those depths. We're showing, because this is intentionally a complex well, we're showing that we're actually drilling through a producing zone in the field, and you're taking the well on deeper. Down at the bottom, we show the potential for loss returns that has shown itself on several wells that have been drilled. Over to the right is the fracture gradient, or this is the pressure in pounds per gallon that would be required at that depth to initiate a fracture into the rock. The dashed line that you see over here is the mud weight that is expected for drilling the well, which is about a half a ton higher than the core pressure. And the little dots on the right is what we call the design frac gradient, or it's a safety factor on what the fracture gradient actually is at that depth. And this is to allow for tripping, to allow for ECD and things like that, and not crowd this line. Now, the typical conventional way that casing is designed is after surface is set, primarily based on regulatory requirements, and also having a frac gradient that is what we need to be able to go into the transition zone down here. The well is, the surface casing is drilled out, the leak off is done to see that we are somewhere in the vicinity of this curve, and then the drilling progresses along the mud weight curve. When the mud weight reaches what the fracture safety gradient point is at the surface casing chute, it's time to set casing. This process is repeated below this point by drilling out again, checking to see that the frac gradient is in range. Then you drill with mud weight until you reach that point and the casing has to be set. This is then repeated until the well is taken down. In this particular example, when we get to this point right here, we put in a contingency liner, because if the loss returns is not there, then we would be able to proceed in this particular case. However, we put in a contingency liner at this point to allow for it in the design. Now, after the pipe is, the locations are determined using that technique, the next thing is to design the actual sizes of the pipe at all of these different depths. And this is done from the bottom up and from the inside out. In this particular case, the production engineers will normally tell you the size tubing that you want to be able to produce the volumes and the type of fluid that they want to produce. In this particular case, it's 3.5 inch tubing to about 11,000 feet and 2 7/8 inch on down. So at this point, then the bottommost or the production casing at the bottom would have to be able to house the tubing with the premium connections that it has. As it turns out, in this case, for 2 7/8 inch with PH6 connections, we'd need at least 5.5 inch liner on bottom to be able to accommodate. That liner then will have to have a hole drill that's at least 6.5 inches to be able to do it, and that in turn tells you the size of the casing that you have to set above there to be able to drill that hole. Likewise, this would be 75/8 inch liner, so above this point, we would have to have at least an 8 5/8 inch casing, but we'd rather drill a 9 1/4 hole because of the potential loss returns that we talked about in the prior slide. This would require 10 3/4 casing to be set at this point, and in order to set 10 3/4 casing, you'd need 12 1/4 hole, which would require 13 5/8 inch casing. The next step, after the sizing the casing, would then require the selection of materials to be able to withstand the pressures and the fluid flow that we expect to have. In the case of the tubing, it would be the shut-in pressure and whatever pressure would be required to kill the well. If a tubing leak developed, then the production casing on the outside must be able to contain it. So that's how you design the tubing and the production casing. The protective casing string would have to be would be comprised of the 13 5/8 inch, the 10 3/4, and the 7 5/8 inch casing to drill the bottom. In today's environment, where the Bureau of Safety and Environmental Enforcement for any well that's drilled in federal lands requires you to submit a case of being able to take a massive kit, and when you're drilling the bottommost section of this well, commensurate with what the pressures are, and likely a case where the entire protective casing string, including the liners, would be half filled with gas. This is a real problem in a well like this because, in fact, you can't buy 13 5/8 inch conventional casing at the highest weight and grade that would be able to meet the requirement. So the question then is there a better way to meet this requirement? So here, what we do that's novel is we introduce a new technique that can be used for designing the architecture on the well. On this slide, what you have is the same curves that we just introduced along with the conventional case that we had here. On the far right, we're going to show what the non-conventional design approach would be. In this particular case, you again would drill out some undersurface casing and drill ahead with the mudway following this track. But when we get past the drawn down zone that is shown here, and way before we've even approached what the fracture gradient is at the surface casing, we decide we're going to set a liner. So we'll set a 13 5/8 inch liner underneath the surface casing at this point, which will give us a higher fracture gradient at this shoe than what we had here, which then allows us to drill to the next point and set that where the 13 5/8 inch, we're now able to go an additional 1,000 feet deeper. And now we will set a long string, but the long string now will be 10 3/4 instead of the 13 5/8 inch that we set in this case. The next section of hole would be drilled similarly to what we did here. The 7 5/8 inch would be set there, and then the production liner the same size would be set at the bottom. So what you've got here is that this approach essentially borrows a deep downhole liner for use up the hole to allow setting a smaller diameter protective casing string enough to eliminate having to set one liner at the bottom part of the hole. So we're borrowing a downhole liner, moving it to the top, and eliminating one at the bottom. But the net effect is that now our protective casing string is 10 3/4 by 7 5/8 inch for drilling the bottom, and we can buy 10 3/4 casing with sufficient weight and grade to be able to stand the same hit that we were unable to do if we used the conventional case. The architecture design chapter includes appendices with all of the equations and the resulting load curves that are required to design both the conventional and the unconventional case that we've shown you here. This will include all the way up through the selection of the weights, grades, and connections for the two cases. Now, as the well architecture design is being developed, the design engineer also needs to formulate a well construction design plan to determine what each section of hole how each section of hole should be cased. This is whether you should set a long casing string or whether you should set a liner, and also the procedures that are required to achieve the section and the drill ahead objectives for each section of hole that you have just drilled. The design plan should be driven by formation isolation requirements, such as protection of fresh water or consideration for potential impact of cross-flow between formations that are left behind pipe. Should be based on the cement quality expectations, such as barrier requirements that you actually have and require of that string. One of the most important ones, if not the most important one, is well control capability throughout the process of completing the section. And also to have a balance between cost versus risk between the options that are available. Now, there's always risks associated with drilling and completing wells. Anybody that's been in drilling very long will know that. And when different design options exist, there's going to be different risks that go with each. Making the right choice between the options requires a clear understanding of the consequences of failure to meet the well's completion or well control objectives without having to force the issue. Luck should never be a component of engineering. Taking a higher risk when appropriate. Maybe it was up there too long. Taking a higher risk. This is an important point. Everything that we do has risk, but when taking a higher risk, when it's appropriate, should only result in risking higher costs if things go wrong, and never well operations integrity, which can jeopardize safety of the operation and the personnel. A major portion of the first part of this chapter on well construction design and chapter 8 on cementing technology discuss the importance that cementing plays in well design and the safe and effective drilling and completing of a well. The procedure described and recommended in these chapters result in a list of best practices for displacing mud from the hole and replacing it with cement, and with reducing or eliminating contamination of the cement by the wellbore fluids. Of equal importance to achieving an effective cement job, if if not more so, is the work that has been done to understand the mechanics that causes annular gas flow to occur after cementing operations, and to develop effective techniques to prevent gas from entering and permeating through a cement column before the cement has actually formed the seal. The industry has known for many years that when cement is placed in a wellbore and becomes static, it quickly begins to thicken or gel and become self-supporting within the column and against the walls of the hole and the casing surfaces. The gelation process and fluid loss to permeable formations, or from gravity migration of water from the cement, causes a loss of hydrostatic pressure in the cement column and therefore also in the wellbore. If the resulting combined hydrostatic pressure of the mud and the cement column drops below the pressure of the permeable formations in the section, you know what's going to happen is a well influx can occur. This slide shows the results of one of a series of model tests done in the late 60s and early 70s to investigate the pressure behavior of a cement column in a controlled environment with no possibility for fluid loss from the slurry. The model consisted of a 20-foot pipe section that was open at the top with pressure transducers positioned to be able to read at 3 different points. These are these little P's. After the pipe was filled with cement, heating tape near the top of the column was then used to accelerate the setting of the cement in much the same way that occurs in a real well when you cement it down hole. The hottest portion of where the cement is placed is not at the bottom of the column, but up above. You're actually cool at the bottom part of the hole. So we had heating tape located in the middle of it. As the data shows, the pressure at all depths, which are the red line, this one being the deepest one, begin to drop almost instantly after it was placed in there and before really any of the heating actually had taken place. This occurred steadily throughout, and by the end of the cycle, at around past 300 minutes, 40% of the column pressure had been lost at the bottom of the well. Different models, besides just this one that I'm showing you, using different slurries, and even one that we did with an impenetrable membrane in the cement, so you still had pressure communication, but could not allow the water to move out of the cement, confirmed that the pressure loss was due to both the gelation process and from water migration to the column due to gravity. Subsequent field tests that were reported in an SPE paper in 1983 by Cook, Cluck, and Medrano, where they put transducers on the outside of actual field wells when they were being cemented, confirmed what the model had shown. In early 2010, API brought together a group of cementing experts in the industry in an attempt to better define the parameters that impact cement column pressure decay and to update guidelines to help prevent, and this is in quotes, this is what they set out to do, help prevent and/or control flow just prior to, during, and after primary cementing operations. The results from the group produced API Standard 65-2, second edition in December of 2010. The group used studies, experimental data, and field results to develop an empirical method for estimating when the static gel strength of the cement placed in a wellbore reached a point that they call the critical static gel strength, which is when the pressure decay in the column of cement will be enough to cause the highest pressure formation in the wellbore to become underbalanced. The underbalanced situation occurs when the combined hydrostatic pressure of the mud above the cement and the now decayed cement column pressure no longer provide an overbalance on the potential flow formation in that section of hull. If the slurry gel strength is very low, opposite the potential flow zone, when the underbalance condition occurs, then the well can invade the wellbore and flow through the weak cement. Standard 65-2 provides guidelines on the gel strength that's required to mitigate gas flow through the column. This graph shows an example of the hydrostatic pressure decay of a 1,000-foot column of cement placed in a well as the gel strength development occurs. The pressure loss in the column of cement above a potential flow zone in a well is a function of the column height, the effective diameter, which is the space between the outside of the casing and the side and the hole that it's in, and the gel strength of the slurry. Sometimes changing the variables can result in an acceptable solution to the underbalance situation. Other times, it will be more difficult and the risk of influx will exist. Having a well bore with a high overbalance of pressure provided by the drilling mud above the cement presents the best case for cementing a well without a high risk of angular flow, since the pressure decay of the cement will have less impact on the total column pressure. But even in the case of high initial overbalance on the formation, it is still necessary to do the critical static gel strength analyses that I described from 65-2 to design the job to ensure that an underbalanced situation can be avoided. This chapter will fully develop this complex topic and use detailed examples to help the reader understand how well conditions and job design variables impact risk and well completion options for isolating a hole section. Now, rather than taking the time to get into the math and the option details on this topic, I decided that there would be a greater value by addressing having a high risk annular gas flow in a well when cementing a section should impact well design. Let's look at a worst case scenario where the risk of well following cementing operations is high, discuss what causes it, and then look at how the well design and operations procedures should be selected and implemented to address the risk. This is an example of a well drilled below an existing casing into a section with high pressure hydrocarbons on bottom, likely the production zone. The upper formations right out from drilling this casing are low stress and vulnerable to loss returns. They're weak. Maximum mud weight allowed without a risk of losing returns when drilling resulted in only having a 200 psi overbalance on the hydrocarbon zone on the bottom. The margin between losing returns and having an influx is very narrow. There will also be risk of losing returns during cementing operations because the cement density is going to be higher than what the mud weight is. And then after the cement is pumped in place and becomes static, we're going to have to deal with the gel strength issue that will reduce the overbalance even more. So what are the section completion requirements? What do we want? We want a cement barrier above the producing zone, obviously. And we also are vulnerable to interzone flow, so we need isolation between these two zones. And more important than anything else is we need to make sure that we have well control capability until the section is secure. So the section then should be completed with a liner using a rotating liner hanger without an integral packer, which has an open annulus so that the full hydrostatic head of the mud above the cement can act on top of the liner to be able to maintain a full hydrostatic head all the way to the bottom of the section that we're worried about. Also, the critical static gel strength technology should be used to design the cement job. Okay, so why do we need to do this? Well, first of all, following along the red dots, is a rotating liner will help break up the gels and reduce the equivalent circulating density to reduce our chance of losing returns, and also give you the best possible displacement efficiency. After pumping the cement job with some excess volume above the liner, as we're showing here, and bumping the plug, the setting string should be pulled a short distance above, as we've shown here, above the liner where the cement, and then reverse circulated so that any cement that was drug up by the setting tools can be reversed out. This operation should be conducted while holding a small amount of pressure above the hanger. Well, you will, because if you're reversing, the pressure drop in the tubing is going to give you that while you're getting rid of the cement. The setting string should then be pulled an additional one stand above there so that you leave everything above there has been cleaned out by the reversing process. And then you should maintain the string in the hole until the cement has set. The setting string will serve to test the job both ways after pulling out of the hole, or to kill the well if necessary, because the well decides something didn't go quite like we had planned down here, and we've got a downhole well patrol situation. Now later, after the well is cleaned out, you're able to install an additional barrier on top of this liner by setting either a liner top packer, or if needed, you'd have a tieback because the string above there would not be capable for production. The cement job should be designed using the critical static gel strength analysis procedure to design a two-slurry cement job consisting of a quick setting tail slurry across the hydrocarbon zone that will come up only a short distance above the producing zone. And the lead slurry above there, the darker green one, is a slow gel strength buildup and delayed setting time slurry just all the way to the top of the liner. The lead slurry should be designed, that's this green slurry right here, so that it can maintain an overbalance pressure differential by acting like mud, more like mud than cement, because the gel strengths are very low. And this would be right at the top of where the tail slurry is setting up. This is done until the tail cement has developed strength to seal the potential flow zone. Later, when the lead slurry sets above there, it will provide a barrier in the annulus from the top of the tail slurry all the way to the top of the liner, where you can once again test this job and run a liner top packer and have yet an additional barrier if that's what's required. This chapter and related appendices present many examples of different well section scenarios to consider, along with the indicated well-designed procedures and the equipment required to provide the best possible approach for securing a well section safely and efficiently. At this point, what I would like to do now is turn the program over to Doc Leon, who will handle the rest of the program, and then we will handle questions at the end of the presentation. Thank you.
Most of the rest of this book is developed initially for an on-site drilling workshop for drilling superintendents who had at least 10 years of experience. And we'd spend about a week on the rig, move galley out, sleeping quarters, give them information, the technology, and then they go do it. It was a wonderful way to teach a class. It was the opportunity to do this. Now, many of the projects that we had that are captured in this book, and during the last few years, many advances have been made, and those field-tested techniques have been included in the book. As one indicated, we don't have time to discuss all the technology in this book. Juan talked about planning the well architecture, the well construction, the cementing procedure. Now let's talk a little bit about how a well is constructed with the rig operating at the maximum potential. Most of this book has been about the rig's on-site supervisor. But when a bit is put on bottom, break a rock, make hole. Weight's applied to the bit, the drilling rate increases. This is a drill-off curve. It was published by, initially by Reuben Feenstra and Van Leuven, two great shell engineers from The Hague. Normally with a roller cone bit, we apply extra weight on the bit, lock the brake, and watch the drilling weight go off. The drill string is elastic, so every time you lose 1,000 pounds or 1,000 feet, you know exactly how far the bit's moved. So we've got a good drilling rate. The problem is, if we do that with a roller cone bit, the drilling fluid will clean the tooth. If you do it with a PDC bit, the bit balls up, you have to pull the bit to clean it off. So we can't do this curve that way. This was a problem. Now, what we found when we started doing this is that we could start adding with a PDC bit, add a little bit of weight. What's the torque? A PDC bit responds to torque and rotor speed, not weight on bit. Roller cone bits correlate with weight on bit and rotor speed. But as we increased each one, that are the either weight on bit or the torque, we get to a point where suddenly the drilling rate ceased to go up. This they designated as the founder point. This is the point at which the bit teeth are regrinding cuttings, and an increase in weight on the bit does not create the same increase in drilling rate. Well, how do we detect that? Well, let's go back and look at efficiency. Efficiency is output divided by input. And about in the same time that Reuben Feenstra published his work, a guy named Teal published a paper with the drilling of the W7R bit in the Rocky Mountains tunneling. The W7R bit was an old used bit, very short teeth, no sealed in bearings, a roller cone mill tooth bit. It'd probably be classified now as about a 341 IEDC bit. But this paper was pretty much ignored in deep well drilling because rock failure at the surface is grossly different from rock failure at the bottom of a well. Matter of fact, we have an entire chapter on rock failure in this book. It describes the differences in behavior of the rock itself. But about 40 years after he published a paper on mechanical specific energy, it was resurrected and applied to PDC bits, or polycrystalline diamond compacts. And what to do is plot the inverse of the efficiency. We got the energy input, we know that. We don't know what the energy output is. But we do know the result of putting more energy in, that's drilling rate. So if you compare the energy input to the rate of penetration, you've got basically the inverse of an efficiency curve. Okay, so as we chart up, this thing stays pretty much constant every time you increase bit loading a little bit. The drilling rate increases, the ratio stays pretty constant until we get to this point. Now, the inverse of the energy, you're not using the energy efficiently. So the bit could either be vibrating at the bottom, which we find frequently, or regrinding cuttings that are not removed from the bottom. Well, that means we probably need to improve the hydraulics. You're not getting cuttings off the bottom. So, how do you increase the hydraulics? How do you increase the impact load at the bottom of the hole? You pump more fluid? Well, that would seem to be an obvious solution, but it's wrong. Because I want the pressure drop across these nozzles to be the maximum value I can get. I want the impact load of the fluid hitting the bottom of the hole to be the most it can be, or the power at the bottom be the most. As I pump drilling fluid down the drill pipe, the faster I go, the more the pressure drop. Because the drilling string is a whole series of tubes with two joints. Pressure drop in laminar flow is proportional velocity. Pressure drop according to the turbulent flow is proportional velocity squared. We don't know how much turbulence we have in the drill string, so we have a problem. But what we also find is that if I plot the flow rate and look at the hydraulic impact is force times velocity, flow rate times velocity. That's the force getting to the bottom of the hole. Over here, if I plot force times velocity, or rho QV squared, I get hydraulic power. Okay, let's think about just a minute. You got some mud on your driveway. Take your garden hose out, take the nozzle off, hold it over the mud. You're going to have the maximum flow rate you can get, but it's not going to move the mud off. So you put your thumb over it and get the finest stream you can get with the highest velocity. You don't have much flow rate. It will move the mud up a little bit, but not transport it. So you move your thumb over so that it goes from a low flow rate up to a higher flow rate and a lower velocity until you get to a maximum. Now, the equations for this thing is complicated, very confusing. But the equations are derived in the appendix of each chapter. We've tried to separate out the practical operations in the main part of the chapters and put all of the math in the appendix so that you could, if you're interested in drilling engineer and you're interested in where those equations came from, go back and reproduce the derivation. But for a driller on a rig, it doesn't need to know that. The driller needs to know, how do I get this thing at peak? Well, we take all of those equations and massage them whole page full and reduce it down to a real simple thing. I know what the flow rate is. I know from the optimum pressure drop, in this case, this would give me the maximum hydraulic impact, the maximum force of the fluid hitting the bottom of the hole. U is a unique constant for each well. That is, it depends on many, many factors. It depends on how much of the flow down the pipe is turbulent, how much of it's laminar. Well, if I'm circulating a very thin fluid, turbulence extends a long way. If it's a very thick fluid like pudding, it doesn't go very far. It depends on the temperature of the drill string. It depends on the crossovers I've got in the string. I mean, if I have a downhole motor, I have NWD tools, it depends on all of that. This values vary from 1 to 2. The procedure for determining it is very simple. Four measurements that a driller can make on the circulating bottoms up just before you pull a bit. And you can design your next bit so that it will either hit, the fluid will either hit the bottom of the hole with the most force or the most hydraulic power. As a side note, many years ago, there used to be a lot of argument about which one was best. And as far as I can see, no one has ever run a real comparison between the two. So both procedures are put in here depending upon what your philosophy is. So I maximize the hydraulics. Now our founder point moves up to here. Well, what controls that? Well, our hydraulics depend on the drilling fluid. To remove the cuttings from the bottom, that drilling fluid has to have the lowest possible velocity, or viscosity, so it'll have the highest velocity. This is required for getting the button cuttings off the bottom of the hole. So if I take out the drill solids and I reduce the viscosity, I can raise the founder point on even higher. Now, to transport the cuttings up the annulus, I need a drilling fluid that has a high viscosity. It sounds like magic, doesn't it? Drilling fluid suddenly changes from a low viscosity to a high viscosity, and that's because we adjust the viscosity because it is a rheologically complex fluid. It is a shear thinning fluid, that is, the faster it moves, the lower the viscosity. And so we can adjust the viscosity in the annulus to make it clean the hole. But the way we decrease the viscosity through the nozzles at the high shear rate is to have as few solids in the mud drilling fluid as possible, which means you have to remove the drill cuttings. Now to do that, then we need to process it. We need to get them off bottom. We need to transport them to the surface as carefully as we can. And then we need to process the drilling fluid at the surface. Once the cuttings are at the surface, the solid control equipment has to remove them. The secret to trouble-free, fast welds is to remove those evil drill solids. As Juan mentioned, cement strangulation means that cement has to displace drilling fluid. Now, a drilling fluid, cement will not displace a very thick filter cake. Long-term loss of production behind casing will result in loss of millions of dollars of production because of the failure to create a cement barrier in the production zone. And this again is the failure to remove the drill solids. Another thing, the fluid in the drill string must be the same density so that if you get a kick, you'll know what the pressure at the bottom of the hole is. If you have different density of fluid in the drill pipe, the surface measurement for a kick is incorrect. Now, there are a lot of additional subjects that are presented in this book. Safely and efficiently enhance rig performance. For example, we talk about mud logging operations, we talk about pressure integrity tests. The drilling suggestions chapter contains many lessons that we've learned over the past several decades of drilling. But one continuous theme permeates this book, and that is eliminate drill solids. And to accentuate this theme, I would like to bore you with the first 4 minutes of a recent presentation I made, which hopefully will communicate this concept. The paper on the economic consequences of poor solids control. I have a moment of quiet silence, please. Friends, we're gathered here today to consider the evils of drill solids.
Amen.
Unless you believe you will suffer the torture and the torment caused by drill solids. For our text, I select the 12th chapter, section of the Driller's Knowledge Book, which says, "And lo, the evils of drill solids were upon them. 4 plagues were visited upon their heads. There were combs lost in the hole. Lost circulation was emptying the drilling fluid from the pits. Drill pipe was sticking, requiring a round-the-clock supervision. Sunrises and sunsets blurred together. The drilling cost was attracting the attention of the wise men in the East. Let not drill solids break your heart. These devilish plagues follow drillers who fail to believe that drill solids are evil. Drill solids are insidious and sneaky. Then the true nature of drill solids is revealed. You will suffer these unspeakable tortures if you fail to believe. The path to trouble-free drilling is through the elimination of drill solids. So I say, repent, yield to good bentonite, so that bentonite may yield for you. Verily, verily, I say unto you, rejoice, for in this century equipment has been given unto you, which shall remove the evil drill solids from your drilling fluid. This century, the instructions were well recorded for the diligent believer. Repent, for unto you is given this day a manual, which shall be a guide to all people. With its guidance, you shall eliminate the evil drill solids from your life and reap the glories and happiness of clean drilling fluid. Apply these simple rules, and untold riches will be granted unto you. Enjoy the greatness of clean drilling fluid, and the glory of clean drilling fluid will shine in the hearts of all drillers once they recognize the evils which drill solids shall inflict upon them and their seeds for all eternity. Drill solids are evil. Repent, reject drill solids.
Amen.
Amen.